exercise 24. So this is exercise from linear algebra. This explains the phenomenon in matrix multiplication. So suppose you got a real 2 by 2 matrix, which means all the entries are real numbers, but suppose it has an eigenvalue which is a complex number, lambda equals a plus bi. Let's say b not equal 0. Then in this case there will be a phenomenon that if you consider this linear transformation from R2 to R2 by mapping whatever vector to this matrix under this matrix multiplication, and you would find that if you continue or if you iterate this operation, the trajectory of this would involve rotation. So let me take an example for you. If we take a to be 0.5 minus 0.6, 0.75, 1.1, let me just tell you the result. If you compute the characteristic polynomial, you will get there is eigenvalue, complex eigenvalue, and so let's conjugate this again eigenvalue, which means you got complex eigen vector correspondingly is conjugate will be vector for lambda bar. And if you use some numerical computation, you will see that, for example, let me take this to be the real plane. You start with any, for example, 0, start as our x0, which I mean, okay, and then you apply this matrix multiplication A. If you keep tracking of it, you will see that there is kind of rotation, but rotation not in the shape of circle, but ellipse. Can you explain this phenomenon? So the secret hides in the fact that, let me put it as follows. If A is real 2 by 2 matrix, similarly, just to state my result, let me denote this eigenvalue to be a minus bi. Then I'm saying that by changing basis for R2 to the real part H, imaginary part of the eigen vector, and then this matrix could be described by this matrix C, changing basis, the imaginary of V and real part of V, so both are just real vectors, which means vectors in R2, fixed basis, and then under the changing basis, your matrix A will change to this matrix C, and this C, the result tells you that it is this A minus B and BA. Okay, so let's first see what are this result telling us. The first remark is that so A minus B, B of A is actually a rotation composing with a scaling. If this is zero matrix, then nothing to say, trivially this is true. If it's not zero, denoted by R, square root of A square plus B square, and then here we have this square root of R plus square root B over R equals 1, and so this equals some cosine theta, this equals some sin theta. We could got this. There is some theta, unique theta inside. Let's say minus pi to pi. Okay, and so this is actually just the rotation by theta. Second remark. So the situation is as follows. I'm explaining this changing basis just. So this is multiplication by A, which if it's equals P, say P inverse, then this is just telling you that start with any vector. Instead of map it to AX, I could firstly map it to B coordinate under the basis B, which I'm fixing it to be image real part of V and imaginary part of V. It's a new basis. You could show that the new basis basically is because that V and V conjugate, because it corresponds to different eigenvalue, so they're linearly independent, and obviously the span of V and V bar is the same as the span of real part of V and the imaginary part of V, as the basis of the span complex vector space. Okay, and you can show that this is the basis of R2 also. And so what we do is, here we got our C. So this is mapped to C x bar of beta. And this is changing basis. It's given by multiplication with P. And then finally you kind of prove that by multiplication by P, and you got your previous vector. And so the C is described by T of the first vector in real basis. Take the B coordinate, and then second vector real basis, take the B coordinate, and then this is your basis. See, sometimes we denote it by B bracket B, and you could show in this case, just check it is indeed given by the form A minus B BA, just by direct computation. Okay, this also gives you a proof actually of this theorem just stated. And so how to explain that phenomenon? Actually, it's after you change your basis, you got new coordinate system, and then there your matrix transformation is just this rotation. But when you translate it back to your to the vector itself, or translate it back to the standard basis, it's because of this real partial with and imaginary partial with not orthogonal normal basis. And so there would be kind of dish shaped into an ellipse, not a circle.